to the IMS Tweedy New Researcher Award. The award was created with funds donated by Richard's friends and family. And a new researcher is one who received their doctoral degree in one of the 5 years preceding the nomination. And the recipient of the award is Adel Javanmard, who will deliver the next presentation. Let me tell you a few words about Richard Tweedy, whom I had the honor to meet. Richard was an outstanding Australian statistician who contributed to the field of applied probability and modeling in statistical science. Richard was an international scholar working successfully both in the private sector as well as an outstanding university administrator. I met him when he was chair of the University of Minnesota Division of Biostatistics while I was a PhD student there. He joined University of Minnesota after being chair of the Department of Statistics at Ohio State University. The most fun memory that I have of Richard was at an MCMSKI conference. Together with to compete in the famous ski race. And we won the prize for the team with the largest variation in the time to complete the race. Richard was not a great skier, but he was certainly very courageous. He sadly died prematurely at the age of 53, my current age. So a few words about Adel. He's an assistant professor in the Department of Data Science and Operation at the Marshall School of Business at the University of Southern California. Prior to joining USC in 2015, he was a postdoc at the Center for Science and Information with work site at Berkeley and Stanford University. He completed his PhD at Stanford, advised by Andrea Montanari, and his research interests are broadly in the area of high-dimensional statistics, machine learning, optimization, and personalized decision-making, and we will hear more about it shortly. Adel is the recipient of several awards and fellowship, including, besides the Tweedy New Researcher Award, the SNF Career Award, the Google Faculty Research Award, the Thomas Cover Dissertation Award from IEEE Society, and the Douglas Brazil Award for Junior Business Faculty, among others. So without further ado, let me leave the stage to Adel. Thank you.
Okay, thank you very much for the generous introduction. And hi, everyone. I'm Adel Javanmard from the University of Southern California, and I'm really honored to present this year IMS Tweedy Lecture Award. As we all know and heard, Richard Tweedy had a very profound career, and he had made significant contribution to different domains and branches of statistics, from convergence analysis for Markov chains, from queuing theory to system theory, to Bayesian statistics, to methods for epidemiology, and the list goes on and on. It's really a great pleasure and honor to receive the award in his name. And I would like to thank the award committee for choosing me for this year's recipient of the award. Today I'm going to talk about reliable statistical inference for high-dimensional models. And this is based on several papers that my colleagues and I finished in the past few years. So I would like to start by thanking my collaborators. The first and foremost, Andrea Montanari, my former advisor at Stanford University, Yash Deshpande, who is a postdoc at MIT, and my student at USC, Mohammad Mehrabi. Okay, great. Before I continue, I would like to say that this is almost midnight in Los Angeles, so I apologize if the lighting is not perfect. but I try my best to be as energetic as possible. This is a unique experience for me, giving talk at midnight, but hopefully it will go quite well. Okay, to set the stage, we are living in the era of data deluge, where we can collect massive amounts of information and data at very fine-grained scale, very, very easily on a daily basis. And because of this eruption in data collection technology, we are also observing that quantitative methods and statistics are used in different domains, from life science to physical sciences, to economics, to finance, to business application and e-commerce, where the firms use the machine learning algorithms to improve their revenue, to better target their audience, to come up with better policy for pricing and advertising. And the list goes on and on. Probably the most relevant example to the current pandemic situation is developing drugs and vaccinations. And we know that the statistics plays a key role in this process to make sure that the drugs that are going to be delivered to the market are statistically significant in terms of improving people's health, and they can provide some virtues rather than hurting people. And we see that statistics have been used in all of these domains. I think it's fair to say that the foundation of such a widespread application of statistics has been created in the previous century by worker Ronald Fisher and many other great researchers who contributed significantly to modern statistics and also to experiment design. They basically operationalize a framework for people to do science. So this is the hypothesis-driven approach to science, where you ask some question, you formalize some hypothesis, then you test your theory on the data. And based on the outcome of your experiment, you can decide whether you should reject your theory or you fail to reject your theory. The outcome of the experiment, as we know, is not always black and white. It's not 0-1, and it contains some fair amount of uncertainty. So statistics here, the role of a statistics is to understand and interpret the uncertainty that you observe in the outcome of the experiment, and to convey your result as exactly as possible to the other people. Uncertainty in the outcomes of the experiments also make life challenging. Probably the most important challenge is the reproducibility challenge. What do I mean by reproducibility? Suppose that I have some theory and method, I run it on some data set, and I find some interesting discovery. Let's say my method says that there is some association between a specific gene and susceptibility to a specific disease. So this corresponds to, let's say, in my model, one of these parameters that they have is non-zero. So there is some association between this gene and this disease. Now, this is an interesting discovery, but I want that if someone else take my theory and method and run it on a different data set, they should also be able to see the same discovery, not exactly, but at least up to a statistical error. So this is what we mean by reproducibility. And of course, we want the science to be reproducible. We don't want to be the only person who can observe our discovery. We want the other people to also be able to replicate the experiments that we have. But what we hear in the literature and the media is that the science is becoming less and less reproducible. And the media literature is full of different alarms. I'm sure that many of you have already seen many of these heads up that the science is becoming less replicable. So here I gathered a bunch of these alarms from the literature. So this is a paper by John Ioannidis from Stanford. It has a kind of provocative title that's saying that most published research findings are false. And in this paper, which is very influential and highly cited, he explained in a very simple way that what are the most common pitfalls and mistakes that people do in analyzing data sets, which leads to coming up with many, many false discoveries. The other example, for instance, is this paper, which was published in Science. And what they do in this paper is that they take 100 experiments. These are basically the studies that have been published in the top 3 journals in psychology, and they try to replicate the result of these 100 experiments. 7 of these experiments had already reported significant results. So the p-value for those individual studies were each of them less than 0.05. So they looked at 97% of these discoveries are significant, but when these people try to replicate the same experiment, only 36% of them could be reproduced. The other discoveries somehow vanished into the air. The other example is this paper published in Nature. In this paper, there is a study by Amgen, which is a company in California, and it takes 53 studies that were considered to be landmarks in basic cancer science. So these are the papers that have been published in top journals like Nature, Science, and so on. And they try to replicate, again, the outcomes of these 53 studies, but only 6 out of them, like almost 11% of them, could be replicated by Amgen. The other discoveries were not observed again in the other experiments. And probably the most relevant example, again, to the current pandemic situation is when you are doing this different phase for developed drug and vaccination to offer to the market. You see there are different phases, phase 1, 2, and it goes on. And each phase, it becomes more stringent, and you want to make sure that the drug that you are delivering is really helpful for people. So when you get to phase 3, you should be almost satisfied with your drug, almost confident. But we see that, again, in this report, 22 of these drugs that survived to phase 3 failed to phase 3. So they were considered to be significant and effective in phase 2, but when they go to the phase 3, they are not significant and they don't have that effect on that experiment. So again, you see that if you make a mistake here and you mistakenly come up with a drug and say that it can be helpful, but it's not, then it could have a catastrophic result and outcomes on people. And you see the media and literature are full of different stories trying to alert about the reproducibility crisis that we are facing. What's interesting is that we are facing this reproducibility crisis exactly at the same time that we have a good technology for collecting data. And this coincidence is not just by chance. You can argue why these two things are happening at the same time from different angles. So one argument is that because of the availability of data, the way that people are doing science has been quite shifting from a hypothesis-driven approach to data-driven approach. So in hypothesis-driven approach, which was very common in, let's say, 15, 20 years ago, people come up with some questions, some hypothesis, they collect the data, and then they test their hypothesis on the data. Based on the significance level that they get, either they reject their theory or they fail to reject. But nowadays, data is available everywhere. People are constantly exploring data, and then they come up with some interesting pattern in the data, and they ask the question. So the difference between data-driven and hypothesis-driven is that in data-driven, you first collect the data, and based on the exploration of the data, you formalize your hypothesis, and then you test your hypothesis. Data-driven approaches are completely fine as far as you account for different source of bias and uncertainty in your analysis. But as a matter of fact, most people don't do this, and that's one of the reasons that we see so many false discoveries. The common mistake, which is very, very simple, is that they use the same data set to formalize the hypothesis and also to test the same hypothesis. And obviously it has bias, so it could give you many false discoveries. The other one is an interactive data analysis. So you see the same nature, but in a more subtle way. Like we know that there are many public data sets that are shared by researchers, and many different teams are testing their hypothesis on these data sets. But the hypothesis that people come up depends on the data set, exploring the data set, and also the outcomes of the previous hypotheses and methods that have been tested on that. And because of that, there is a large correlation, dependency among the hypothesis, the bias that comes from data exploration, and each of these teams might report some statistically significant finding. But when you think about the overall picture that many other teams are also trying the same data set with different hypotheses. You are facing a multiple hypothesis testing problem, so you need to control for the overall uncertainty and the false discoveries. But of course, for many of these public data sets, there is no central unit to control for the sort of family-wide error rate or the false discovery rate when many people are using the data sets. What can we do about the reproducibility crisis? Well, there have been some response from the community, like journals and conferences now require people to share their codes and data to improve the reproducibility of the results. There are different initiatives where you can submit your data and also the method and ask them whether they can also try on different data sets and make sure that the results that you found are indeed reproducible. Some part of the issue for the reproducibility crisis is the culture in the academia that people have some like urgency to publish interesting findings, and they don't report the failed experiments. Because of those culture, we also have some problem on that part, but again, I don't think there is much can be done in terms of changing the culture, at least in the next few years. The question of interest that the statistics community have been trying to answer is how to come up with new statistical methods to enhance reproducibility. And this question has initiated a long list of interesting research topics in the past few years. So I've listed some of them here, the most relevant one to this talk. So among them is the debiasing for high dimensional statistical inference that I also would spend time to explain the debiasing method. The online control of false discovery rate, which basically says that you have a stream of hypotheses coming in and you want to test this hypothesis, but you don't have any information about how many hypotheses you will have, which could be infinite number of hypotheses, and you don't know the future p-values that you get. But you want to somehow control the false discovery rate in an online manner. So this is somehow to stimulate what's happening for research findings where many people are testing their hypothesis and you don't know how many other teams would come up with new hypotheses, but you want to have some control over the false discovery rate in an infinite horizon. The other line of work is the selective inference that have different branches from post-selection, adaptive, interactive inference, the cheating, the p-hacking, data snooping. And I would like to take this opportunity to say there is an interesting seminar on selective inference organized by Rina, Will, Lihua, and Daniel. And there are many interesting talks on selective inference with the same spread. So if you can register the mailing list, there are many interesting talks on that part as well. The other line of work is the knockoff framework for controlling false discovery rate and variable selection in high dimensions. So what I want to do in this talk is I want to spend some minutes on debiasing, the classical debiasing, and what is this method for high dimensional statistical inference. Then I will go to debiasing outside the IID world when you have adaptive data collection, and introduce something called online debiasing, and then see how we can use that to do inference for high dimensional time series. Okay. So the first part, the background on debiasing, is based on these papers. And let me start by a concrete example. Suppose that you have n data points. Each data point is a pair of yi, xi. Yi is sort of the response or the label of interest, and xi is the covariates or the feature vector that you have. So as an example, you can think that yi is the glucose level of patient I, and xi is the p-dimensional feature vector that summarizes the medical record of that patient. So you can think that it's constructed based on the medications that the person is taking, the lab result, the diagnosis, the history of medication. And here I'm taking a data set from Kaggle. It's posted by Practice Fusion company. And from this data set, I'm taking 500 patients. And based on their information, I'm making around 800 features for their as the feature vector based on their medical information. This is a simple example just to convey what we want to do by statistical inference on high dimensional models. The question that I want to answer is, given this data set, I want to see what are the important features that are relevant to the glucose level. What are the features that are significantly relevant to my response of interest? And you can ask the same questions in different domains. For instance, you can, if you are working with GWAS, genome-wide association studies, you want to see what are the significant SNPs for specific disease, let's say the risk of diabetes. Or for instance, what are the important factors based on the record of people to see whether this person would reoffend to somehow gauge for the recidivism risk. The other example is that if I give you the record of the person who has applied for a loan, what are the important factors? What are the factors that are significantly relevant to see whether the loan could be paid off or not? And in these examples, I want to highlight that these are not predictions problems. Like in the first question, to understand the significant features for the glucose level, I don't want to predict the glucose level. I can easily measure that one. The question that I'm asking is more about the association. I want to see what are the statistically significant features that are relevant to my response of interest. Like, is, I don't know, smoking statistically relevant to glucose level or not? Or I don't know, drinking coffee, does it have something to do with the glucose level? And I can prove it if there is some statistical significance or not. So these are the sort of questions that I want to answer. To make it a bit more concrete, suppose that we have some statistical models. So the response of interest yi is coming from some probabilistic model. So I'm assuming that there is some family of distribution which is parameterized by theta 0. Theta 0 is a vector in p dimension, it's unknown. And then once you have this family, yi is coming from this f of theta 0 condition on the features xi. And this theta 0 is somehow encoding the importance of different features, different entries of this xi in your response of interest. So what I can do is that I can try to fit a model to this data based on this family, this parametric family that they have. So in this example, I'm taking the response to be the glucose level. I have the features. It's a high dimensional problem in the sense that the number of samples that they have, n, is lower than the number of features, p. And to recall, u was 500 and p was 800. So what I can do, for instance, is I can fit lasso estimator to come up with some estimate data I have of the model. And because of the L1 penalty, you see that here, most of the entries of my estimated model is 0, but there are some non-zero parameters. And you can interpret different coordinates of theta to somehow tell you what's the importance of that feature in predicting response y. So you get these values of theta that are non-zero. But if I do the same thing, but on a different data set. So instead of working with this data set, I resample people from the Kaggle data set and I try to fit lasso again, then I get another set of parameter estimation. If I change the population, again, I get another different set of estimation. Another question is that if you run this method on a data set and you see that some of these parameters are non-zero, how can we trust that they are really non-zero? How can we trust that there is some statistically significant association between the corresponding feature with the response of interest, with the glucose level? Because every time that they change the data set, these estimates of the importance of the variables are going to change. Okay? So how can we rely whether we found something interesting, some association or not? You can formulate this problem as hypothesis testing problem. So the null hypothesis is that the ith coordinate of my model is 0, which says that there is no association between variable I and the response of interest. And the alternative is that it's not 0. And I want to come up with valid p-values for this hypothesis testing problem. Okay? So I want to have the p-value that under the null hypothesis, they are uniformly distributed. Or I can use the duality instead of working with the hypothesis testing. I can work with the confidence interval. So I want to come up with some confidence interval for each of the individual parameters in my model so that the coverage is at least 1 minus alpha. And of course, I want the length of the interval to be as small as possible. Now, these two questions require to have some distributional characterization of the estimate theta hat if I want to answer these questions either in form of the hypothesis testing or confidence interval. And it seems to be something classic in statistics. So why is it hard? The answer is the high dimensionality of the model. So if you are in the low dimensional setting where you have a fixed number of variables and the number of samples is going to infinity, you can, for instance, take the maximum likelihood estimator and then use the large sample theory and show that it has a normal distribution. And once you have the distribution of theta hat, you can construct the p-values and confidence interval in the usual way. But when you go to the high dimensional setting where the number of features, the number of variables is much bigger than the number of samples, then the life becomes a bit challenging. First of all, you cannot directly go with the maximum likelihood estimator because here the number of unknown parameters p is bigger than the number of observations n. So there's no unique solution to the maximum likelihood estimator, and you often require some sort of regularization. Like the specific case for this formulation is like lasso, where the log likelihood would be the quadratic error, and this regularization would be the L1. Now, if I want to characterize the distribution of theta hat, then it becomes challenging. I cannot use the large sample theory because the perturbation sort of argument that is used in the large sample theory wouldn't apply here. First of all, theta hat minus theta 0 is not negligible. And second, this regularization R is often non-smooth regularization. And because of this, I cannot use this sort of perturbation argument to show that theta hat is normal distributed. Indeed, theta hat is biased because of this regularization. Because of this regularization, the estimate theta hat is sort of having a tendency to go to the region where this regularization is small. Okay. So the question, the obstacle here is how to come up with a distribution and characterization of theta hat, your estimator, which is a regularized estimator in high dimensional setting. Okay. So the specific example is like the lasso estimator. But if I fit a lasso in a high dimensional model where p is bigger than n, what's the distribution of theta hat? Okay. So this is the question. And we know that this is notoriously hard, and you can only characterize the distribution of lasso in some specific cases of design and the error. So what can we do? What's the idea of the debiasing? So let me start with the low dimensional and a very simple example. Let's focus on the linear regression, where y is given as a linear function of features. So y is x theta 0 plus noise. And in this case, if n is bigger than p, the easy estimator is the ordinary least square estimator. And we know everything about the least square. It has an explicit formulation. It's given by 1 over n, the inverse of the empirical covariance x transpose 1. And the useful property of the least square is that it's an unbiased estimate of theta 0. So if I plug in for y here and I simplify, I get that the least square estimator is theta 0 plus this term, which is a Gaussian noise. Now, once you have this nice unbiased estimator and you know exactly what the distribution of this estimator is, you can compute the confidence interval and do hypothesis testing. And the sort of confidence interval that you get for each of the coordinates would have the length of like order 1 over square root n. So everything is good in the low dimensional setting. So what breaks if I go to the high dimensional setting? The first problem is that I cannot even define the least square in high dimension because sigma hat is not invertible. Sigma hat, again, to remind you, was the empirical covariance. So it's a p by p matrix, but the rank of sigma hat is n. and n is lower than p. So sigma hat is not inversible, and I cannot even define the inverse of sigma hat. So I'm stuck in the first stage. So what can we do? Let's do something similar to see what other estimator we can get for the high dimensional setting. I cannot define the least square because sigma hat inverse does not exist. But let's say I choose some matrix M, and you can take your favorite M for the moment. We then discuss what's the right choice for M. And then I define an estimator called theta hat star in an analogous way to the least square. So it's 1 over n. Now instead of this quantity that doesn't exist, I use matrix n, x transpose y. And then I plug in for y, recollect the term, and then I get this decomposition. So my estimator theta hat star is the true model theta 0 plus a biased term plus a Gaussian error. Okay. So far, so good. The problem is that, okay, I have a biased term here, and I want to get rid of this bias. In the low dimensional case, the choice was, okay, take M to be sigma hat inverse, and then you can obviously kill the bias. But now sigma hat is not inversible, so I cannot fully make this term M sigma hat minus identity 0. I cannot get rid of this. The other problem is that theta 0 appears in the bias, and theta 0 is an unknown parameter that I would like to estimate, right? So I cannot subtract bias. But what I can do is that instead of working with theta 0, maybe I can work with another estimator of theta 0. And the choice here for high dimensional linear model is lasso. So instead of theta 0, I use the lasso estimator, and then I try to subtract bias from this theta hat star. So I get theta hat d, which is basically the theta hat star that they had, minus, this is sort of an approximation of the bias that they have here. So instead of theta 0, I'm using the lasso estimator. And to remind you what was theta hat star, again, theta hat star was 1 over n m x transpose y. So if I plug in for theta hat star, I get this formulation. And this is called the debiased estimator. So D here, the superscript D is for debiasing. So it's basically saying that you start with the lasso estimator. It has bias because of the L1 penalty. But I add a term to somehow compensate for the bias. But of course, when I add this term, the lasso estimator is not sparse anymore. So somehow I'm trying to transform bias into variance. And this transformation is done through this matrix N. So by this additional term, I'm removing some of the bias, but I'm adding some variance. But if I do it properly in a correct way, in an optimal way, maybe I can remove the bias, and then I can characterize the distribution of this theta at D. And once you have the distribution of the debiasing estimator theta at D, you can continue from there and construct the p-values and hypothesis testing. Okay, so the question is how to construct this matrix N. So this is the decomposition that we have. We have the debiased estimator minus the true model theta 0 can be decomposed into a bias term and the variance term. Conditional on X, I know that this Z is coming from a normal distribution, and I know exactly what the covariance of that is. And the bias, again, depends on the matrix M. So what's the right choice of M? Ideally, I want to make the bias to be 0. So I want to reduce this term. I also want to make the noise variance to be as small as possible, because the variance of the noise is determining the length of the confidence interval. Or if I'm doing the hypothesis testing, the power of the test would depend on the noise that I get here. So I want to make both of these terms as small as I can. So what I can do is that I can write a quadratic optimization for matrix N. The objective is I look at the noise term here. The variance of the noise, different coordinates, is given by M sigma at M transpose II, the II coordinate. So this is the variance of the ith coordinate, and sigma square, I don't have control over it, so I drop it in my optimization. I want to minimize the maximum variance of noise. So this is sort of minimizing the worst case confidence interval length for the coordinates. And I want to have some constraint over the bias. So I don't want the bias to be very large. So I want to control the bias. For the bias, if you look at the bias term here, you have a term m sigma hat minus identity, and then you have basically the error of less. So if I use like Cauchy-Schwarz, I can take the infinity norm here and the L1 norm here. There are great results on controlling the L1 estimation error of regular estimator. So I have a control over the L1 norm of this error. I need only to control the infinity norm of m sigma hat minus identity. And this gives me an optimization to construct matrix M. How should I choose this constraint, the upper bound gamma, n, and p? It depends on the design. If you're working with a fixed matrix X, it depends on like some sort of a coherence number for the design. But if you are working with random design, the right choice for this gamma, n, and p is something of order square root of log p over n. And once you solve this optimization problem, you have the matrix M, you plug in for your Debiased estimator, and you get something nice that is unbiased asymptotically, and you know what the distribution of theta at D is. So this is the theorem that we have. Basically says that theta at D minus theta 0, it has a noise part Z. The distribution of Z given X is completely characterized. And the bias term that you have, you can control the infinity norm of the bias. And it's something like S0 log P over root N. What's S0? S0 is the number of entries in the parameter theta, which are not 0. So theta 0 is a vector in P dimension. So let's say P is 800 in the example of cholesterol glucose level. P was 800. But of course, you don't expect all of the covariates to be relevant to the glucose level. Probably a few of them, like 20 or 30 of them are relevant. So S0 is the number of non-zero coordinates in the model. So this is the bound on the bias, and it tells you that if this term goes to 0, so if n over S0 log P squared goes to infinity, the inverse of that, then the bias would be little o of 1. So asymptotically, you would get rid of the bias in your estimator, and then you have something very nice, which is normal. And this is going in an analogous way with the maximum likelihood estimator in the low dimension. So this is sort of a surrogate for the high dimensional case. And once you have that, you can construct the confidence interval in the high dimensional setting. And the length of the confidence interval that you get in the high dimension is, again, order 1 over root n. If you compare with the least square in the low dimensional case, it's also 1 over root n. So it's matching the length of the interval. And you can prove that this is optimal in certain ways, like in the minimax way, it's an optimal length of the interval, or if you're formulating it as a semi-parametric efficiency, it's also optimal in that way. So the difference between the length here is that in the low dimensional case, you have the inverse of the covariance. Here, if you're working with random design, you have the inverse of the population covariance. So instead of the empirical, you go with the population. And one thing that I want to highlight is that this debiasing framework that I explained does not require like the irreproducibility or beta mean condition for those people who know that are common for support recovery. Okay, you don't need those assumptions for inference. Okay, so I want to spend a few minutes on like the required sample size. Here, if you look at the theorem, what I need is that S0 log P over root n should go to 0. So it's already telling me that how many samples I need to do valid statistical inference in a high dimensional model. I basically want this quantity n over S0 squared to go to infinity. But if you think about estimation task or prediction task in high dimensional setting, the number of samples that you require grows linearly in the sparsity level. So as far as n is bigger than S0 log P, you would have like L2 consistency in your estimation and also consistency in the prediction error. So the question is that, do we really need the number of samples to grow like quadratic in S0? Or even if n is growing like linearly in S0, I can still do valid statistical inference. So all of these works on debiasing, but these are from almost 4 or 5 years ago. The analysis requires n to grow like quadratically in S0. And the questions that we are interested in, can we do like a statistical inference when you have linear growth in terms of S0? So we have 2 positive answers, and depending on the setting. So in this paper, we focused on Gaussian design. So Gaussian design means that your design metric X has IID rows, and the rows are coming from a normal distribution with covariance sigma. And then we take the debiasing approach and did some sharper analysis of the bias and variance of this estimator using a leave-one-out technique. So this is a technique to control sort of dependency between different coordinates of the estimators. I spare you the details of the leave-one-out technique, but using this technique, we could prove that if sigma is known to you, you can still get valid statistical inference using debiasing as far as n is bigger than S0 log p square. But this is great because n now is growing linearly in S0. And if sigma is unknown to you and you're required to sort of estimate that or do this statistical inference without knowing the covariance sigma, then apart from this condition, you also require n to grow like S of omega squared, where S of omega is the sparsity of the precision metric, the inverse of the covariance. Yeah. But to keep things simple, if we focus on the known sigma, it tells you that n should be just linear in S0. The other piece of information that we got in terms of the required sample size is through something called approximate message passing, AMP machinery. So we focus on standard Gaussian design. So X has IID rows coming from standard normal. And instead of working with the classic debiasing, we define something that's slightly different. And the difference is in this coefficient. So previously it was 1. Now it's 1 over 1 minus the L0 norm of the estimator divided by n. So this is sort of a degree of freedom adjustment. And we show that if you go with this adjustment, as far as n, p, and S0 are of the same order, then you can still show that theta hat d is unbiased and follows the Gaussian distribution. Okay. So this was a rigorous proof for a standard Gaussian design. We also use non-rigorous argument based on replica method from statistical physics to show that if you go with the same degree of adjustment in the general case where like X is coming from Gaussian design with covariance sigma, then this degree of adjustment is also important if you want to do statistical inference in a regime where n, p, and S0 are of the same order. Okay. But this is, of course, non-rigorous. It's based on replica method. So I wanted to also mention these 2 very recent work that take this degree of freedom adjustment and do some rigorous analysis and showing that if you are in the regime that, again, n, p, and S0 are of the same order, this degree of freedom adjustment is required for debiasing to give you valid confidence interval and p-value. Okay, so this was background on debiasing. So in the few minutes that are remaining, I want to discuss how you can extend this to outside the RAD world. So what do I mean by RAD world? The setting that I explained the debiasing was where you have n data points. Each data point was yi, xi, and these data points were coming IID from some unknown distribution. And this is the common assumption that's usually made in the statistics community, machine learning, and so on. But in many areas of application, the data is not IID, and this IID assumption is clearly violated. So one example is when data is an expensive commodity, like in clinical trials. In these cases, you want to be very careful on how you are choosing your samples in your study. So you look at the previous outcomes of your trial, and based on the outcomes that you have, you select who should be the next sample that they want to include in my study. Basically, I want to go with the samples that are most informative about the trial. And because of that, data points that I get would be adaptively collected. They depend on the previous outcome. The other example is the time series and the panel data. So if you think about the stock market, for instance, the value of the stock that you see today, of course, depends on the previous day, and they are correlated. They are not IID. The other examples is the bandit problems, where you have an agent that's interacting with the environment. At each step, the agent takes some action, and based on the action, gets some rewards. And these rewards tell the agent that what should be the next action. Now, the observation that the agent has from the environments are basically the rewards over different times, but these rewards are dependent because each reward depends on the action that you took, and the action that you take at each step depends on the previous reward. So all of these rewards are correlated. Now, you see that this adaptively collected data setting is prevalent in different domains. So let's focus on a linear case. You have yi is xi transpose theta 0 plus epsilon, but xi depends on the previous data point. So xi at time I depends on the data that you have from time 1 to I minus 1. Another question is that if you are given this adaptively collected data, can you do consistent estimation of the model? So this is the first question. And this question is quite simple, and you can observe that in different domains, you have the consistency property because the data that you collected are naturally giving you more information. So as you go on and make more samples, you collect enough information to have a consistent estimation. But the other question, which is a bit subtle, is that can we do statistical inference with adaptively collected data? And why is it challenging? Because because of this adaptive collection of the data, you have some sort of endogenous bias and correlation in your samples. And because of this bias, statistical inference becomes also more challenging. So if you think about this problem, for instance, in a high dimensional case, you have two sources of bias. One source of bias was because of the high dimensionality of the data and like the bias of the lasso or other regular estimator. The other source of bias is because the data points that you have are collected adaptively. Now it becomes more challenging to do a statistical inference. Okay, so let me tell you what happens on debiasing if you want to apply it in this setting. If you take the debiased estimator, again, to recall you, this was the formulation for the debiasing, and M was constructed by this quadratic optimization. What the argument was that you have this bias variance decomposition. I try to remove the bias, and then you have this term. And since M and X are independent of epsilon in an IID setting, I can use the central limit theorem and say that it's normally distributed. But if you think about an adaptively collected setting, even if I can kill this bias term here, the noise term here is not unbiased anymore. Because again, M was constructed based on sigma hat, and sigma hat was X transpose X. So M depends on X. But since the data is adaptively collected, X also depends on the noise. And this makes that M and X both depends on epsilon. And because of this dependency, this term, the last term, also has some bias. So I have two sources of bias. How can we deal with this? So I give you the gist of the idea on how you can deal with this part. The idea is that when you are constructing M, instead of looking all the samples together, instead of working with the entire matrix X, I use these samples in a gradual way to control the correlation between M and epsilon. So if this term, this is the noise term that I have, instead of using the same M for all the samples from 1 to N, at each step, I use a different matrix MI. but I want MI to be measurable with respect to the previous sample. So MI should be in the, let's say, sigma algebra of the previous data points so far. But if MI is measurable with respect to this, then it becomes independent of epsilon I, because epsilon I is the error that's observed at time I. This error is independent of the previous data, right? So if I can somehow make sure that MI only depends on the previous data point, not all of the xi, then I can make sure that this term here is a martingale. And once you have a martingale here, you can come up with different settings that this martingale is stable, and then you use the central limit theorem for the martingale and show that it goes under some Gaussianity assumption. So the trick here is that in construction of M, you use the samples in a gradual, in an online way. How much time do I have?
You have another 5 minutes.
Another 5 minutes. Okay, great.
Say
So I'll go quickly over how we can come up with these matrices MI and what would be the application in time series. So I take the data points from 1 to n. I divide them into different episodes. So these are different chunks of the data. What's the length of these episodes? I take them to be generic, and then I optimize over the length of the episode. So what happens at the end of each episode, I construct a matrix n, only using the previous xi, only using the previous feature vector that we observed. And then I use that matrix to debias the future sample in the next episode. So M1 depends on the observation in episode 0, and then it's used to debias the sample in episode 1. M2 is defined based on the sample from episode 0 and 1, and then used to debias the sample in episode 2, and so on. Okay. So this way I make sure that the MI is measurable with respect to the history, and then it's used to debias the future sample. Okay. How should I choose the length of this RL, the length of this episode? I need to compute what would be the bias of this estimator in terms of the length of the episode, and then optimize so I can make sure that the bias has the optimal rate of going to 0. So one important example of this is in high dimensional time series. So let's say you have a vector autoregressive model. You have vector in p dimension z of t, and then you have this linear form that tells you how this vector is evolving over time. So you can think of this ZT, for instance, to be different stocks, and you want to see how the value of the stocks would change over time. These matrices here are unknown in your model, and you want to estimate them. But if I tell you that one of these coordinates, like ij entry of A, is non-zero, it means that the value of stock I today would have something to do with the value of stock J, let's say tomorrow or 5 days from now. And if I can do statistical inference, it means that there is some statistical significance between these two values of the stock. Now, this is, of course, an example of adaptive data collection. So what I can do is I can use the online debiasing and do confidence interval and the testing. So I can make sure that whether there is some correlation between these two or not. So I see that the time is almost done. So let me show you a numerical example on autoregressive models. So I'm taking P to be 15. I have like observations of this var D model over 60 periods, and the lag of the model is 5. And these are the histograms that you get if you do the classical debiasing versus the online debiasing. You see that these are the QQ plot and the PP plot. If I go with the classical, like the vanilla version of debiasing, there is some bias, and they are very far from the Gaussian distribution. But if I do the online version of debiasing, so I carefully control the correlation between M and epsilon, then I can make the histogram of the online debiasing to follow a normal distribution, which ensures a valid statistical inference. Okay, with that, I would like to conclude, and I would be happy to take if there is any question.
Thank you, Adel. Very interesting. I particularly like the debiasing as a way to transform bias into variance, and this leads to the classical variance-bias trade-off that we often face in statistics. And the solution that you propose is a minimax type of solution. So I have one question. There's a question from the audience as well. But my question is, has anything been done in the Bayesian approach towards solving this issue? Well, we know that Bayesian statistics was one of the interests of Richard Tweedy, together with Markov chain and Markov chain Monte Carlo methods. So in the regularization term in the lasso can be reinterpreted as a prior. And so I'm wondering whether, rather than doing minimax in the Bayesian approach.
Exactly. So the debiasing approach that I presented was mostly in terms of the frequentist version of like p-values, where you assume theta 0 is fixed and the data is random, and then you want to do inference on that one. But as you said, if you interpret like the regularized estimator to in a Bayesian setting, that the prior is coming from the regularizer, yes, you can do also statistical inference on that framework. But the usual criticism is that why the prior is like the regularizer. Like if you do the lasso estimator, why the prior is Laplace transform, right? So the L1 corresponds to the Laplace prior.
Right.
So these are two different like approach to statistical inference. So this was mostly the frequentist version.
Yeah, sure. So we do have a question from Jonas Krampe. The question is, do you know how sensitive is the debiasing technique to the choice of the tuning parameters?
How sensitive it is to the choice of? It's a very good question. So this vector, this parameter that you choose to control the bias, the way that we do in the implementation of the debiasing, if you check the code, is that we do some binary search. So we want to make this, let me go back to the optimization. So I want to make this coefficient here as small as possible. This gamma n of p, I want to make it as small as possible. But if I choose this to be very, very small, then this optimization problem is not feasible. So in implementing of the debiasing, we do a binary search, and we try to go with the smallest threshold here so that this problem is feasible. So in this way, we are minimizing bias as much as we can. We squeeze it as much as we can, and then we see what would be done in terms of the objective. But if you choose gamma not to be very small, then of course some of the biases remain there.
Good, thank you. If there's, yeah, we do have 1 minute for another question. In the time series setting, do you let the number of episodes go to infinity?
Okay, the number of episodes, yeah, can go. So the only constraint is that the length of the episode should add up to n, but you have control. So n is going to infinity, and so the number of episodes can also go to infinity. But so the only constraint is that they should add up to n, but how can I choose each of these episodes? It depends on the bias. So what we get in the paper is that, like, if you go with the exponential growth, so if let's say the length of the episode doubles each time, then it gives you the best rate for controlling the bias.
Good, thank you. And well, let's thank Adel and